Hello there. Today we look at magnetohydrodynamic power generation. So, that is the topic for today's class. Well, let us look at some of the terms right at the title slide. So, we do have this term hydrodynamic. So, if you are a mechanical engineering background student or even otherwise you may have encountered this term. Essentially it has got to do with the fluid flow, with the movement of say some mass in the presence of a fluid, relative movement of the mass with or some object in the presence of moving fluid, and that is what that study is then referred to as the hydrodynamic study of that combination of some movement of this liquid and this mass. So, that is hydrodynamics, relative movement, study of the relative movement of solid in some fluid flow. So, that is what you are looking at, hydrodynamic behavior. Now, we are additionally adding something here, magnetohydrodynamics. So, there is some fluid flow here. So, as you can imagine from this terminology, there is some fluid flow here, there is some magnetic field here, and there is some relative motion. So, all these things are going to be there in the concept that we are going to discuss through this class, and it is associated with power generation. So, and that is the relevance of this topic to our course. Now, I will also point out that people have studied this, and there is still some work that goes on it. However, it is not still that commonplace, and there are competing technologies, there are issues with this technology, etc. So, it is not something that, and that is the reason why most of us are unlikely to have heard about this. So, it is for example, this is so this is abbreviated as MHD, but chances are most of us have not really heard about it, or heard about it as something significant. You do not really read too many articles about it in the general public parlance, unlike say lithium ion batteries or any other such technology which you are hearing about all the time. So, that is something to keep in the background. So, although we will look at this for a sort of a sake of completeness kind of activity, and it does have some relevance in the grand scheme of what impact it is making, it may not be as significant as of at least as of today. Okay, so we will learning objectives for this class are to look at the operating principle of magnetohydrodynamic power generation, and we will also see that there are different modes in which it can be implemented. So, we will briefly look at those different modes in which this magnetohydrodynamic power generation can be implemented, and of course, in the context of this discussion we will look at the challenges posed by this technology and try to get a sense of what is possible here. Okay, so, those are our learning objectives: the operating principle, the different modes in which the magnetohydrodynamic operation happens, and what are the challenges posed by it. So, if you see what do we normally do in terms of a large scale power generation plant. In a large scale power generation plant, you have some fuel, and that fuel is burnt. Okay, so, it is burnt to release that energy, and so that energy then moves this way. Okay, so, from fuel some energy is coming out, that energy moves this way, then it heads off towards some generator. So, maybe let us say turbines that rotate, and that is connected to a generator, and then we get electricity, right. So, our output is electricity, input is some fuel which is then burnt, then moves through this process and generates electricity. So, when you do this, as we are aware, since it is like a heat engine kind of a process, you have this thermal energy that is coming and you are converting that to electricity after discarding some amount of heat. The efficiency is given by 1 minus T2 by T1. So, we are sort of limited to this efficiency, and therefore, it is in the scope of this efficiency that we pick up energy from the fuel. So, there is some energy in the fuel, we pick up that energy. So, there is always interest to see if there is some little extra energy that we can squeeze out of the fuel over and above this this limitation. This limitation is there, but is there a way to work around it? Is there a way to do something before we reach this hit this limitation, etc. And so, that is something that we are interested in always looking at. So, as I just said, our the typical thermal power plant, that is our scheme of operation. So, we have some hot gas that is coming in, and that is essentially sent towards a thermal plant, and in the thermal plant we are generating electricity. So, that is the general scheme of operation that we have, and as I just mentioned, this is our efficiency limit. Okay. So, that is basically what we are trying to do. So, as I said, our intention is to see if there is something extra we can do in this circumstance to get a little bit more energy out of this fuel, and any extra energy that we get out of the fuel essentially increases our overall efficiency, overall process efficiency relative to the energy that is available in the fuel is only going to go up if there is some way we can squeeze out some more energy from this process, right. So, this is where we create this, we utilize this magneto-hydrodynamic generation process. Okay. So, this MHD process is utilized in this context. It is the magneto-hydrodynamic energy generation process is used in this context of utilizing the process flow that is already happening in a thermal plant and sort of introducing this into that process flow to see if you can extract some more energy out of that fuel. So, basically now what we do, instead of going from the hot gas directly to the thermal plant, which is the turbines essentially, and where you generate the electricity and then you get the electricity out of it. Instead of doing that, the hot gas first goes to this magneto-hydrodynamic generator, and from there it goes to the thermal plant. So, this is the pathway it takes, right. So, first to the MHD and then to the thermal plant. So, in fact, they call this as the topping cycle and sort of the bottoming cycle. So, at the top end of this cycle of the movement of this fuel, we pick up some energy, that is the MHD cycle, and then the thermal plant comes right after that, and that is the bottom half of this cycle. So, usually the MHD is operated in this mode in a combined cycle power plant. Okay. So, typically it is not really operated separately. Of course, for study purposes you can operate it separately and that may be the best way to operate it even, but generally you are looking at a combined cycle power plant, which is where we generate this energy. So, it is in this context that it is utilized. Okay. So, to do this process, to operate this magneto-hydrodynamic generator, we actually need to create a plasma. Okay. So, we need to create a plasma. So, what is plasma? Plasma is actually it is considered as the fourth state of matter. Okay. So, we are more familiar with solid, liquid and gas. So, these are the three that we are more familiar with. Plasma is the fourth state of matter. Okay. So, it is basically you can think of it as an ionized form of gas. It is gas in an ionized form. It is only in the form of ions that it is present, and it has its own behavior associated with it, and it is actually the fourth state of matter. So, interestingly, I mean the reason again we do not hear about it much, we do not talk about plasma much, because for the most part on our planet we are not really dealing with plasma. Okay. So, you have to go to fairly high temperatures or fields, high electric fields, etc., to create this plasma kind of a situation. Normally in the commonplace activities that we deal with, for the most part on the planet we do not see plasma. For the most part we are not really encountering it on a daily basis in any of the activities that we do. Typically we do not see plasma. Interestingly though, if you take the universe as a whole, even if you take the solar system and you take the universe as a whole, plasma is the most common form of matter. Okay. So, it is easily considered as the most common form of matter. It is there across the universe. There is a lot of ionized material around the universe. So, for example, in all the stars, in the sun for example, the temperature is so high that the material stays in the ionized state. So, in the sun we have plasma, and if you look at the mass of the sun, mass or volume of the sun, well over 99.5% of the mass of the solar system is the sun, right. So, 99 point whatever, more than 99.5, maybe 99.9% of the mass of the solar system is the sun, rest of it is all very small relatively speaking. So, if you look at it that way in terms of mass or volume, even with respect to just our solar system, if most of the sun has this plasma in it, clearly plasma is the most common form of matter in our solar system. Okay. So, that is something that is unusual to most of us because we do not see it on our daily basis, and so something that we do not see on earth that much is what is most common in the universe. So, across all stars, wherever you associate matter with stars essentially, and all the stars have plasma. So, in that sense it is a very common state of matter. So, actually the solid liquid gas that we are talking of is the most uncommon state of matter. So, actually we should call plasma as the number one state of matter, everything else should be less common. So, but that is uniquely with respect to our experience, it is the other way around. So, it basically consists of ionized gas. So, that is what plasma is, and so if you want to create plasma, so you need to get to high temperatures, as I said you can put high fields etc. to create plasma, but if you want to create plasma easily, you need to have elements in your stream which have low ionization energy. Okay, so generally I mean, given the various options, if you are trying to create plasma, if you have a material that has a low ionization energy, you have atoms of a particular kind which have low ionization energy, then those atoms can be converted into plasma much more easily than other atoms which have high ionization energy. So, where you have to put in a lot of energy to get those electrons off. And in that context, cesium and potassium have relatively low ionization energy. If you look at the periodic table and you look at all the elements and see what all ionization they have, cesium and potassium have relatively low ionization energy, and I mean, there are some other elements in between which also have low ionization energy, but they may be rarer to find. So, these are relatively in comparison to at least some of the other elements, these are much more available, and they are easily ionizable. So, incidentally we do have plasma is also of different kinds. It depends on when I say high temperature, the temperature does not even have to be uniform across the plasma. You can have a situation when you talk of plasma, you are talking of ions and you are talking of electrons. So, okay, so you have ions and electrons. So, once you create plasma where you have this ion separated from the electron and the electrons are moving around, the ions are moving around, they do not necessarily have to have the same energy. Okay, so, you can have electrons having much higher energy, the ions having much lower energy. You will have some average energy, but in general you can have a situation where much more of the energy is being held by the electrons, much less is being held by the ions, and so on. So, in that case, so you can have plasma that is somewhat cold, you can have plasma that is hot, lot of different options are available here when you talk of plasma. So, we do have plasma related electronic devices that we utilize. So, some of these lamps which have some vapor in them and then they are giving you the light, they all have this ionized form of matter plasma. So, you do have some of the lighting systems that we use are based on plasma, some of the display systems that we use are based on plasma. So, so plasma is there in some of the devices that we are using, although we may not have consciously understood what exactly we are referring to when we are talking of plasma. Okay, so it is available, it is a fourth state of matter, it is ionized gas, and if you are trying to ionize cesium or potassium, it may be easier. So, you can get plasma out of it much more easily. So, what is that relevance of plasma with respect to magnetic hydrodynamic power generation? Okay, so what we are trying to do is essentially create a situation where we have this fuel that is burnt, and so you get high temperature gas that has been generated. So, that is the first part of our energy generation process, that we send through some passageway, and then eventually we arrive at this power turbines and generate power, turbines etc., and we generate power. So, there is another process that is there later on where we are generating power. Now, there is you have the option that before this hot gas goes to the regular thermal plant cycle, where you have this turbine and you are doing some various activities associated with that, before you get there, you can see if you can get some energy out of this hot gas, because it is already hot. And we spoke about plasma, where basically you can ionize some material. So, intention in this, or the principle behind this magnetohydrodynamic power generation is to take this hot gas and introduce into it the atoms such as potassium and cesium. These will then ionize. Okay, so they will ionize, and then so now in that gas stream, why do they ionize? They ionize because the gas is at high temperature. Okay, so because the gas is at high temperature, the electrons and ions will separate out, and so you have an ionized gas. And so this ionized gas is now moving in a stream. If now you apply a magnetic field perpendicular to the direction of movement of this ionized gas, you can get the ions and electrons to deflect. Okay, so that is the basic principle. You get the ions and electrons to deflect, they may deflect in different directions because of the charge that they have, and in that process you will generate a voltage, that voltage you can tap. Okay. So, this process, these individual steps that I put together here, this entire process is then referred to as the magneto-hydrodynamic power generation process. So, you ionize a gas, you get it to go through an area where there is a magnetic field, and because of that magnetic field the ions and the electrons move in different directions and you generate a potential difference. So, that is the basic idea. So, the burnt high temperature gas is there and you have introduced say potassium or cesium, and then you have this magnetic field here. So, the magnetic field now is into the plane of the display that you are seeing. And so then the electrons and ions, so you will have E minus and you will have ions which are positively charged, they will get deflected. So, you can get them deflected in different directions. So, you will have them deflecting and you will have them deflecting like that. So, you will have some deflection occurring, and in that process you get the you get a potential difference which you can capture. So, this is energy that is available in the stream, which we are now capturing in a different way. So, what have we done here? We have basically created a situation where the thermal energy that is available in the incoming stream has been used to do some ionization. Okay. So, some amount of thermal energy has been used for that ionization process. So, that created ions. Now, that ions and electron ion electron pair that you had, you use that to generate a potential difference, and using that potential difference you generate electricity. Okay. So, you have picked up some electricity from so some electrical energy has come out of the thermal energy that was available in the gas stream using an ionization step in the middle. Okay. So, you had thermal energy and that gave, from there itself directly you got electrical energy. So, from thermal energy you went to electrical energy by simply including an ionization process in the middle. Okay. So, that is the idea. So, that is in this process. So, that is why this process is explored and investigated, because it gives you a pathway to pick up energy from because your original energy is only in thermal form. So, the you burnt fuel, so you have fuel, the energy is available in thermal energy form, from that only you are trying to generate electricity. So, you could do that by doing all those turbine related activities, all the heat exchange related activities that occur with a normal thermal power plant, and that would be another legitimate way in which you could generate your electricity, except that would be subject to all those limitations of the 1 minus T2 by T1 kind of a limitation efficiency. So, even before you do that, you add one ionization process in the middle, and in that process you change the form of energy from thermal energy to something that is now in the electric form, and then you tap that energy. So, you get electrical energy. So, ions and electrons will get deflected in opposite directions, generating voltage. We will come back to this in just a moment. So, so this is the basic idea. So, you get voltage potential difference now, you will get a potential difference here. And so, you put an electrode here, this is an electrode, and this is another electrode or a current collector. Okay. So, you put two electrodes and you generate a the system has already generated a potential difference. So, then you can tap the electricity, and so you have a load resistor which is your external circuit, and in that process you tap the electricity. So, this is the basic idea, and as I said, cesium and potassium can be added to the gas. The temperature should be high enough to ionize these, right. So, it should be high enough to ionize these cesium and potassium, and this idea of adding cesium and potassium to it is referred to as seeding. To get rain you add seeds to the clouds, right. So, cloud seeding, that is different. Here you are adding potassium and cesium as seeds to generate the ionization process, to enable the ionization process, because they ionize very easily. So, that is the basic idea. So, if you want to look at relative to what we saw a little while earlier, so you have the hot gas coming in, but before the hot gas goes to the MHD, if you just send it directly into a region and you call that you just put two electrodes and you send this hot gas in there, that is not really going to help you in a big way. So, you have to do the seeding, so cesium or potassium, and here you are going to have a magnetic field, and then you have the thermal power plant. So, you get some electricity out of this. So, you have some electricity generation out of this, and then you have further electricity generation out of this. So, you have you are generating electricity in a two step process as opposed to a single step process. You have two steps of electricity generation that is happening here, and therefore, this is interesting. I mean, we are getting one additional amount of electricity over and above what you would have otherwise got, and therefore, your overall efficiency is going up. Now, I must point out that if you look at this situation here, that you have these electrons and ions that are moving in response to the magnetic field that you have put. You must keep in mind it is not as simple as it is shown in this figure, although in principle this is what is happening. In principle this is what is happening, the electron is moving in one direction, the ions are moving in another direction, and then you have a potential difference. But there are a lot of other aspects that we have to keep in mind. So, for example, the mass. So, mass of ion, right. So, mass of ion, so let me put it here, mass of ion is much greater than mass of electron. Right, mass of ion is much greater than the mass of the electron. So, therefore, given the same amount of magnetic field and the fact that it is all coming in the plasma together, the extent to which the ion will deflect it will be a lot less than the extent to which the electron will deflect. The electron will deflect much faster, much more steeply than the ion. So, you may have the ions much more gradually deflecting, whereas you may have the electron deflecting much faster, relatively speaking, right. So, you may have that kind of a situation. The electron may deflect much faster, the ion may deflect much more slowly. So, you may even have some of the ions leaving this region without even reaching the electrodes. So, that is a concept that you have to keep in mind. Also, we have to understand that as the electron begins to deflect, it is not sitting in vacuum, right. So, it is electron that is going along with a plasma that is moving, right. So, when that happens, you may have velocity of the electron in different directions, and based on which direction it is in, the magnetic field can impact it or may not impact it. So, to the extent that there is a component of the velocity perpendicular to the magnetic field, it will start doing this deflection the way we have shown you. And as it deflects, it does not just deflect once and just go straight into the electrode, it will continue to deflect, So, in principle it can actually get into a loop. So, in principle this can start traveling in a loop. Over and above that, if there is a component of the velocity in the direction of the magnetic field, okay. So, if it is already in the direction of the magnetic field, then it is not getting affected by the magnetic field, it will simply spiral along that direction, okay. So, if there is a component of the magnetic field in that direction, so a electron velocity in that direction, because of the magnetic field also in that direction, the deflection is happening like this due to the component of the velocity in this direction, but the component of the velocity in that direction simply pushes the electron further that way. So, it will spiral that way. So, it will just spiral that way and go that way. So, you are having that is itself one motion that is happening. Over and above that, it is going to interact with the ions that are moving there, it is going to interact with the plasma that is moving there, some probability of interaction will be there. So, you have to, it is all statistical, you have to see what is the probability of interaction and so on. So, it will have some interaction. So, the movement can be quite complicated, it is not going to be quite simple, it is going to be relatively complicated because there are many factors here which are impacting the movement of that electron. Over and above that, if you generate a potential also, right. So, you have you end up generating a potential like we saw here. So, we have a potential difference. So, now over and above the magnetic field, you also have an electrostatic field, right. So, because the this I mean this potential has been generated due to, let us say, the first set of electrons that underwent this process. So, the fresh and the next set of electrons that are arriving will see this potential already existing against which will impact the which will also influence the way they move. So, now they are moving in the presence of a magnetic field as well as an electrostatic field. So, number of things are happening here. In addition, you will also have a situation that if the electron is deflecting, right, there is relative to the plasma, there is a movement of the electron this way, and there is also a movement relative velocity. If this deflection had not been there, it would have moved further, right. So, there is some relative movement this way also. So, there is a movement this way, there is a movement vertically down and there is a relative movement horizontally as well relative to the plasma. So, what happens is if you actually want to step back and see, there is electricity in both the direction perpendicular to this movement, original movement of the electron, and also in the direction against the direction of the movement of the electron. So, this is referred to as the Faraday effect, Faraday based effect, which is causing this movement perpendicular to the original direction of flow of electron, and this movement which is happening due to this curvature as it happens in the presence of the magnetic field, and as a result it is moving actually slower than the plasma. This is due to the Hall effect, okay, on the movement of the electron. So, you can sort of see that there can be a potential difference in the vertical direction, there can also be a potential difference in the horizontal direction, generating, if you just look at this region, if you look at this region and you go from left to right, there can be a potential difference due to this Hall effect. If you go from top to bottom, you can have a potential difference due to the Faraday effect. So, it is a fairly complex situation that we are dealing with when you are talking of this kind of a situation where you have a hot gas going, you added something to it, created a plasma, and that plasma is now interacting with this magnetic field, it is generating an electric field, and then both of them are present, and then subsequent atoms and atoms that come there which become ions and the electrons have to deal with all of this or are interacting with all of this. So, it is a fairly complex situation that we have here, but still at the end of it we have a potential which is the potential that we tap, and then we get the load resistor to function. So, if you actually see, we can as I said, the movement of the electrons and the ions will depend on charge as well as mass, right, on charge as well as mass, and that is why we had this movement this way, we had the movement that way, and then even here, so this is electron, that is ion, and then here also we were looking at what is the extent of movement this way, what is the extent of movement in that direction, and so on. So, all of that is happening in this generator at the same time. So, to the extent that we tap the voltage, as I said, there is a potential difference here. Okay, so, there is a potential difference between the top and the bottom of this unit. So, to the extent that we tap this potential difference between the top and the bottom, we refer to it as the Faradaic generator. Okay, so in the context of a magneto-hydrodynamic generator, you have multiple ways in which you can tap electricity even from this this region, this overall region, which is the MHD generator. Within this region, after this it becomes a regular thermal power plant activity. So, and before this is also just the fuel burning. So, in this region you can tap electricity in more than one way. You can think of different configurations in which you can tap electricity, and then they and that usually accentuates one aspect of this process, and then we try to capture it in that form. And so, for example, this manner in which we are capturing energy, where we put one large electrode here, one single large electrode, right. So, this is one way we would do it. Similarly, on top you will also have another single large electrode. So, you put a single large electrode on top and you put a single large electrode at the bottom, and then you connect the external circuit to it, and then you get electricity. So, you connect the external circuit to it, and then you have a flow of electrons, and you generate you have captured electricity, you have generated electricity which you are capturing elsewhere. So, what have we done here? One of the things that we have done and the reason, that is the reason why I am emphasizing this idea that we have put a single large electrode on that side as well as a single large electrode this side. The point of emphasizing that is that as I mentioned, you will also have the Hall effect. The Hall effect is related to the fact that this electron is moving in the presence of this magnetic field, and as a result it ends up having a relative motion with the plasma that was moving. Originally it came with the same velocity as the plasma. Now, because of the Hall effect, it may actually be moving with lower velocity with respect to the plasma, and because it is curving away, and so then you have to look at how much displacement it had in the direction of the plasma. So you have a potential difference that is coming from the horizontal movement of the electron. So when you put a single large electrode, you are sort of smearing that out. Okay, so once you put a single metallic surface there, a single large electrode, you are smearing that out. So you are essentially smearing out the Hall effect. So you are smearing out the Hall effect. So the difference in potential in the horizontal direction is being ignored, and it is is being converted to one flat electrode of a common potential, and from that you are tapping the electricity. So that is what is happening when we do this single large electrode kind of configuration, and there we are only looking at the effect that is in the perpendicular direction, and that is called the Faradaic generator. Now even though you may be doing a Faradaic generator, by doing this kind of a single large electrode and smearing out this Hall effect, you are actually not capturing as much of the energy, because you may have much better potential differences at various locations if you give the opportunity to pick up those potential differences. So what we do, instead of putting a single large electrode on either side of this region, we segment the electrode. Okay, so the process that is used is to segment the electrode, so that you will now have a series of electrodes on top and a series of electrodes at the bottom, and you can pick them up as pairs. So now they are not in electrical contact. So for example, it will look like this. Okay, so I have a series of electrodes on top, I have a series of electrodes in the bottom, and I can pick them up in pairs. So for example, I have shown you one pair, that I have picked up one pair here, right. So I picked up one pair here, which is then connected to this load resistor. Similarly, I can pick other pairs. So for example, I can pick this pair. Then I can pick this pair also. And so on. So I can do that for this also. Right. So we can pick them up in pairs. So and each of them is individually electrically isolated from each other. They are electrically isolated from each other. So therefore there is no it is not a it does not force the potential of that entire surface to be the same. If you have a conducting material, it will force the potential to be uniform across that conducting surface. If the better the conductor, the more uniform the potential will be. It will be difficult for you to sustain a potential difference across that surface, and therefore you will not be able to capture the differences that may exist from point to point. So now on the other hand, each of them is separate. So I can capture this in so many different ways. So I can have multiple generation processes happening, where I take advantage of the fact that even in the x direction, the potential is varying from location to location. So not only is it varying from location to location in the y direction, it is varying in location to location in the x direction. So this is called a segmented Faraday generator. Okay, so this is one implementation in which this the magneto-hydrodynamic electricity generation can be done. Similarly, we can also do a Hall effect generator. Okay, a Hall effect generator is one where we say that we will short out the Faradaic generation process. We will only focus on the Hall effect generation processes. So these are actually shorted out. So these get shorted out like that, and then you actually take the you take the electricity in this direction. So this is the Hall generator. So it uses only the Hall effect generation, Hall effect related potential difference that shows up between the, let us say, the first electrode and the last electrode, and then you get the electricity out of it. So this is the Hall effect generator. There are other implementations also which people look at, which are not really in this mode. So for example, they create a disc. So they create a disc kind of a situation where the fluid comes in the center of the disc and then goes out radially. So you have a situation where the fluid comes in the middle and then goes out radially. This is now going, what the images that I have shown you so far are linear. I mean, it is moving from left to right, right. So it comes in one direction, continues in the same direction. There you change the direction, you come in from the middle and then you move outward radially, and then again you apply a magnetic field and so on, and then you generate electricity. So that is a different configuration that accentuates some ways of generating the electricity, makes it more compact. So these days they focus more on this disk based generation system. So that is again something that people are looking at. So in any case, this is the Hall generator. So these are different configurations in which you can set up this magnetic field with this ionized stream and get it to interact with this ionized stream, and generate this electricity, and that is the manner in which this magneto-hydrodynamic generation process happens. So, to conclude our discussion on the magneto-hydrodynamic power generation process, so the magneto-hydrodynamic power generation process enables us to generate power from hot gases without moving parts. So, I think that is something that we have to emphasize here. Normally we are looking at, you know, in any thermal power plant and so on, you are looking at some moving part. So, that there has to be a moving part eventually. Eventually you will have to have turbines that are running, that turbine rotating, and that turbine has to be connected using a shaft and some gear system to a generator, and there you will have you will have conductors which are which are moving relative to a magnetic field and generating electricity, right. So, at the end of the day there is a lot of moving parts there which are required to convert the thermal energy that is available in your incoming stream to electricity in your coming out of the generator. So, typically we require that, but the magneto-hydrodynamic method of generating power creates a situation where you can get electric power from thermal energy in an incoming stream without having any moving parts. So, we are not talking of the electrons and ions as parts, they are basically part of a gas stream which is moving, and so we do not have any physical parts, solid objects that are moving. So, that is the thing. It requires high temperatures, and here we are trying to our best to get away with the most reasonable amount of temperature we can go to without going too high. Normally you are looking at if you are looking at many of the materials that we would know which we can ionize, you are looking at few thousand degrees centigrade requirement to ionize and create plasma. Here you can get away with a little lower temperatures because you are using cesium and potassium. So, hopefully you can get away with a relatively lower amount of temperature in the scheme of ionization. So, but it is still a high temperature in the overall scheme of things. As I said, it is usually not done in isolation, it is usually combined with a regular thermal power plant, but it appears at the top end of that stream, it appears at the earlier part of that stream, and that is how we first pick up some energy from the incoming stream using a non-moving part process, and without using this heat engine in the conventional sense. We just get electricity straight out of this stream, and then we send it to the thermal power plant. Of course, the only other issue that we have to keep in mind is that it can have implications that are related to toxicity, because you will have some of these ions which will show up in your exit stream. They will be present in the waste material that you generate from this stream. The ash that will that comes out will have cesium, potassium, etc. So, you may need to do some cleaning process to get these out of the stream before you throw out the waste, so to speak. And so, that is an aspect of this technology that you have to pay attention to in the form of during the implementation process. So, that is something that you have to keep in mind. So, that then is our summary of what the magneto-hydrodynamic power generation process is, and as I said, it is not a very common kind of power generation process that that we would be hearing about a lot, and that is the reason why most of us have not heard about it. However, it is something that people are definitely interested in and very keen on looking at, because it increases the efficiency of existing power plants. So, existing power plants efficiencies can go up. However, you are putting in an additional part into the plant, so there is some cost involved in it, and you may also need additional parts to do the cleanup of the ash after it has been generated. So, you may need additional parts. So, there is some infrastructure that is required, some cost involved with that is present here. So, it is not without cost implications, and that is the reason why it has not really caught on, because people look at other ways in which they can improve efficiencies of power plants, and given that there are competing technologies, you have to look at the overall cost implication before you can really consider this as something that you really want to push, and that is the reason why it is still not as widely prevalent as many of the other technologies that we have spoken about. Okay, so that is our summary of the magneto-hydrodynamic power generation, and overview of how it works, and what is the context in which we look at this generation process. So, now this concludes the range of power generation activities and non-conventional energy sources activities that we discussed through this course. So, I would like to spend a few minutes just to summarize what we have done in this course. So, we started off with this one number. We did some initial introduction where we looked at the usage of energy around the world, in particular we looked in great detail at how it varies from nation to nation, how it varies per capita from nation to nation, and also we looked at various things like how does it vary by sector. So, how does the industrial sector use energy, how does the residential sector use energy, how does the automotive sector use energy, which nations use energy more, which nations use energy less. In the nation to nation, what is the difference in the mix of energy that they use, the sectors which use more energy in specific nations, and so on. So, a lot of detailing we looked at of these kind of pieces of information, and we also pulled all this information together by saying that human beings on average are using 500 exajoules of energy each year. Right. So, this is the thing that we saw. We also looked at its impact on the environment. We saw that this idea that we do not make a difference to the environment is actually very misleading, that even in the space of 50 to 100 years you can easily double the amount of CO2 in the environment if you do nothing different. If you just continue in the current manner, you will increase the CO2 content by 100% in just 50 to 80 years, which is well within our lifetime. And the fact that there is a very strong evidence that suggests that if CO2 percent goes up in the atmosphere, temperature goes up. So, in fact, we also looked at the idea that the information that a planet like Venus is so hot because of the amount of CO2 that is present. So, there is overwhelming evidence that carbon dioxide in the atmosphere raises temperature, and this overwhelming is even simple calculation shows you that when you burn fossil fuels at the rate at which we are presently burning fossil fuels, you can double the amount of CO2 in the atmosphere in 50 to 80 years. And also the fact that we already are at a level of CO2 which is higher than what has existed in the planet in hundreds of thousands of years. Okay, so, we have already in the last 50 to 100 years we have reached a very unique situation with respect to the amount of CO2 in the atmosphere, and we are likely to double that in the next 50 to 80 years. So, that is the context in which we looked at this all the technologies that we discussed in this course, keeping in mind that there is a major environmental implication here, and therefore, we need to do something about it, and non-conventional sources of energy offer us many options which are cleaner, and therefore, we should look at them. In this context, we spent a lot of time looking at solar energy because as we said it just comes down on earth, we are doing nothing, it is already falling on us. Most of the time we are complaining about it, saying it is so hot and so on, and but that is energy that we can tap, and if we can tap it nicely, then it is very convenient to us. We have solar thermal energy that we can tap, we have solar photovoltaic energy that we can tap, and this energy is coming down to us roughly at about 1 kilowatt per meter square, that is falling on us. And in fact, every hour we are getting enough energy from the sun that more than exceeds this that matches or exceeds this 500 exajoules of energy that we require for the entire year. So, even with a lot of inefficiency, if we just knew how to tap solar energy properly, all our energy requirements are taken care of in a very nice manner. We then looked at wind energy, we looked at different forms of wind turbines, horizontal axis wind turbines, vertical axis wind turbines. We looked at the limits of efficiency of the wind turbine, the Betz limit, so to speak, and we tried to understand what we can do in this context, how much and also the fact that it is a very benign form of capturing the energy. It is also indirectly a solar energy based system, because the solar energy is what creates the temperature variations which results in this movement of wind across the globe. We looked at ocean thermal energy conversion, where we basically looked at the difference in temperature between the top surface of the ocean and water which is about a kilometer down, and there is enough difference there of the order of about 25 degrees centigrade, and that is there in with large thermal mass. There is large thermal mass that is sitting with this temperature difference, and then even though the temperature difference is not much and that you are going to get only some small amount of energy out of it, the efficiencies are low. Still, because it is just there sitting there and there is nothing else, that is it is a very benign way of in which you can capture this energy. You can keep on doing this, and you can easily set this up so that you can get a lot of energy to augment your energy sources. We also looked at geothermal energy. So, while OTEC is something that is really relevant only for people who are in the coastal area, geothermal energy is really relevant to people anywhere in the world. I mean, anywhere in the world people could use this. Of course, traditionally the use has been closer to regions where there are faults underground, so that you can reach this hot temperatures much sooner. with at much lower depths, and then using that high temperature you can convert water to steam and then use that energy to run a turbine. So, it is very clean because you are not really burning any coal, you are simply using the heat from under the ground. So, that is geothermal energy. We looked at biomass. Biomass basically implies that you are burning plants and trees and some product of plants and trees to generate your electricity, or converting them to some converting corn to some form of liquid fuel and then using it. It has pros and cons because, as I said, on the one hand it is considered clean because you are only releasing carbon that was already captured by the plant, but on the other hand you have issues such as you may be releasing a lot of other gases or environmentally hazardous gases also out into the atmosphere, and the efficiency with which this the plants will give out the energy, or the wood will give out energy, calorific value may be less, and so you may end up burning more of those plants. And also you have to keep in mind that a tree takes anywhere from 50 to 1000 years to grow, and that is how long it has taken to capture all that carbon and sort of sequester the carbon, so to speak. And but when you burn it, the same tree can be burnt in 5 minutes time based on which plant you are putting it to use in. So, you are releasing the same carbon dioxide in 5 minutes, what was captured in say a few hundred years has been released in 5 minutes, and that is exactly the problem that we have now. I mean, it is not that we are suddenly creating this carbon from somewhere, but all this carbon that was captured by the environment, by the earth over millions of years is being released very fast, and that rate of release is just not acceptable. We are not capturing it back at the rate at which we are releasing it. So, in that context this is not a very good form of energy to look at today, even though people will argue that it is zero carbon footprint and all that they will argue, but this is the problem, the time scale is just not the same. If you want to capture all the carbon back in 5 minutes time, you have to plant a huge number of trees. You may have to fill the planet with trees to just capture the same amount of carbon back in 5 minutes. So, that is something that you have to keep in mind. Then we also looked at batteries and fuel cells, which are interesting ways in which we get electrical energy using from the chemical energy, and both batteries and fuel cells are essential in the grand scheme of non-conventional sources of energy, because most of them require most of the other forms of non-conventional sources of energy require some energy storage, require some flexibility in how that energy can be used with time, and batteries and fuel cells play a very unique and important role in that scheme. We also looked at supercapacitors and flywheels mainly because they offer a different combination of specific energy and specific power relative to say just batteries or plain capacitors, and so they fill in the sort of fill in the blanks between batteries and capacitors in terms of serving an energy requirement, and usually they deal with situations where the transition in energy is high. So, you are going from you are suddenly accelerating a vehicle, suddenly applying brakes to a vehicle, and so you want to capture the energy very fast, you want to release the energy very fast. Then batteries are unable to do that. Capacitors can do that, but only for an extremely small fraction of time. So, supercapacitors and flywheels bridge that gap. They give you significant amount of energy released over a period of a few minutes, and that is really what is a few seconds to a few minutes, which is what is necessary in a number of applications where the transition is the important thing that we are trying to cover. Okay, so that is the context. And finally, today we looked at magneto-hydrodynamic power generation, which I told you is an interesting way in which you can increase the efficiency of plants that generate the power plants that generate electricity, but it is still not a very common way of in which it is utilized, but nevertheless it is something interesting that people are looking at, and is at least one of those things that we should be aware of, because that gives you ideas maybe of other ways in which people can try and look at improvement of efficiencies of plants. Okay, so with that we conclude this course. I hope you enjoyed it, I hope you found it beneficial, and I hope it gave you a very good perspective of non-conventional sources of energy. Thank you.